Hello, welcome to Gointamayani. I am HarshaVardhana. In previous session, we discussed some of the importance on geometry representation of a complex number. In this session, we are going to discuss problems on geometric representation of a complex number. Here the one problem said that z is equal to I minus 1 by cos pi by 3 plus I sin pi by 3 into polar form. This problem can be solved in steps. Here we first evaluated trigonometric functions in the denominator, that is cos pi by 3 is equal to half and sin pi by 3 is equal to root 3 by 2. Thus the denominator becomes cos pi by 3 plus I sin pi by 3 is equal to half plus I root 3 by 2. After that we can write the complex number as z is equal to I by 1 by 1 by 2 plus I root 3 by 2. After that we rationalize the denominator by the conjugate of the denominator. Therefore z is equal to I minus 1 into 1 by 2 minus I root 3 by 2 by 1 by 2 plus I root 3 by 2 into 1 by 2 minus I root 3 by 2. In step 4 we calculate the denominator 1 by 2 whole square plus root 3 by 2 whole square, that is equal to 1 by 4 plus 3 by 4, that is equal to 1. So the denominator simplifies to 1. After that we expand the numerator, that is I minus 1 into 1 by 2 minus I root 3 by 2, that is equal to 1 by 2 I minus 1 by 2 minus I root 3 by 2 plus root 3 by 2. Combining the like terms we get 1 by 2 plus root 3 by 2 plus 1 by 2 minus root 3 by 2 into I. In step 6 we write in standard form, thus we have z is equal to 1 by 2 plus root 3 by 2 plus 1 by 2 minus root 3 by 2 I. This is the standard form. After finding z in polar form, the modulus r is given by r is equal to root of 1 by 2 plus root 3 by 2 whole square plus 1 by 2 minus root 3 by 2 whole square. The argument theta can be found using tan theta is equal to imaginary part over real part, that is equal to 1 by 2 minus root 3 by 2 by 1 by 2 plus root 3 by 2. In step 5 we simplify to find theta. Calculating this gives tan theta is equal to 1 minus root 3 by 2 by 1 plus root 3 by 2, that is equal to 1 minus root 3 whole over 1 plus root 3. This simplifies to tan 5 pi by 12. Therefore final answer for the value of z is theta is 5 pi by 12. We move to the next problem. Convert z into minus 1 plus I into polar form. In this we first calculate modulus r. Therefore modulus r represents the distance of the complex number from the origin in the complex plane and is calculated using the formula r is equal to root a square plus b square. For z is equal to 1 minus 1 plus I, the real part is a, that is equal to minus 1, and the imaginary part b is equal to 1. Therefore r is equal to root of minus 1 whole square plus 1 whole square, that is equal to root of 1 plus 1, that is equal to root 2. After this we have to determine the argument theta. The argument theta is the angle the number makes with the positive real axis. Therefore we find it using the relationship tan theta is equal to b by a, that is equal to 1 by minus 1, that is equal to 1. After that, since the real component is negative, a is less than 0 and the imaginary component is positive, b is greater than 0. Therefore, the number lies in the second quadrant, and the principal argument for this quadrant is theta is 3 pi by 4. Therefore, the polar form of the complex number is z is equal to r into cos theta plus I sin theta. Substituting the calculated values for r and theta, we have z is equal to 2 root cos 3 pi by 4 plus I sin 3 pi by 4. Therefore, the polar form of the complex number minus 1 plus I is z is equal to 2 root cos 3 pi by 4 plus I sin 3 pi by 4. Problem. Find the multiplicative inverse of the complex number root 5 plus 3i. To find the multiplicative inverse of the complex number root 5 plus 3i, we have to follow these steps. In this, first we have to understand the concept of multiplicative inverse. Therefore, the multiplicative inverse of a number z is defined in such that z into z to the power of minus 1 is equal to 1. For the complex number, the multiplicative inverse can be represented as z inverse z to the power of minus 1 is equal to 1 by z. In our case, z is equal to root 5 plus 3i. In step 2, we write the expression for the inverse. We write the expression for the multiple inverse of root 5 plus 3i as z to the power of minus 1 is equal to 1 by root 5 plus 3i. In step 3, we multiply by the conjugate. To simplify this expression, we multiply the numerator and the denominator by the conjugate of the denominator. The conjugate of root 5 plus 3i is root 5 minus 3i. Therefore, we have z inverse is equal to 1 into root 5 minus 3i by root 5 plus 3i into root 5 minus 3i. After this, we using the formula for the difference of squares, that is a plus b into a minus b, that is equal to a square minus b square. We can simplify the denominator as root 5 whole square minus 3i whole square, that is equal to 5 minus 9 into minus 1, that is equal to 9 plus 5, that is equal to 14. Thus the denominator simplifies to 14. So finally, we have, substituting back into our expression, we have z inverse is equal to root 5 minus 3i by 14. After that, we separate the real and imaginary parts. We can express the multiplicative inverse in terms of real and imaginary parts as z inverse is equal to root 5 by 14 minus 3 by 14 into I. Therefore, the final answer for the multiplicative inverse of the complex number root 5 plus 3i is root 5 by 14 minus 3 by 14 into I. After this, we find the one more problem, that find the square root of 9 plus 40i. You can find the square root by assuming the result is another complex number, that is x plus yi, and solving the real numbers x and y. For this, here we have to set up the equation, that is root of 9 plus 40i is equal to x plus yi. Square on both sides, we get 9 plus 40i is equal to x plus yi whole square. Therefore, 9 plus 40i is equal to x square plus 2xyi minus y square. Therefore 9 plus 40i is equal to x square minus y square plus 2xy into I. After this we equate the real and imaginary parts. X square minus y square is equal to 9. Call it as equation 1, and 2xy is 40, equation 2. After that we solve the system of equations. From equation 2 we get y is equal to 20 by x. So substituting this into equation 1, we get x square minus 20 by x whole square is equal to 9. That is equal to x square minus 20 whole square is 400, and x whole square is x square. That become, therefore x square minus 400 by x square is equal to 9. For this we have to multiply by x square to eliminate the denominator. Therefore we get x to the power of 4 minus 400 is equal to 9x square. That implies x to the power of 4 minus 9x square minus 400 is equal to 0. Here we substitute x square is equal to z. Therefore z square minus 9z minus 400 is equal to 0. Factoring the quadratic equation, we get z minus 25 into z plus 16 is equal to 0. This gives two possible values for z. Z is equal to 25 or z is equal to minus 16. Since z is equal to x square, it must be a non-negative real number. Therefore z is equal to 25 implies x square is equal to 25, x is equal to plus or minus 5 using y is equal to 20 by x. If x is equal to 5, then y is equal to 20 by 5, that is equal to 4. If x is equal to minus 5, then y is equal to 20 by minus 5, that is equal to minus 4. Combining the results, the two square roots are 5 plus 4i and minus 5 and minus 4i, or plus or minus 5 plus 4i. With this I will conclude this session. After this, one more important, please hear. If you have any doubt or clarification in this video or in this problem, please feel free to reach it out. For who enjoyed the video, consider subscribing the channel. And if you have not watched the video, I will include a link in the description box. Please check it out.